Hello everyone, welcome back to some more quantum mechanics here. So we're going to wrap up quantum mechanics chapter 7 today, and then we'll start talking about chapter 8. So on the next exam, you may expect some stuff from chapter 8, like electron configurations and all that. So just keep that in mind when studying for the exam. So we'll get more practice for the exam doing electron configurations in a bit. Okay? All right. So first, we're going to now do a practice problem where we calculate the uncertainty of the position of an electron. Okay. So a 12 electron volt. So electron volt is a unit of energy. Can be shown to have a speed of 2.05 times 10 to the 6 meters per second. So let's assume that the precision or the uncertainty of this value is 1.5%. So how precise can we measure the position of the electron? So remember, in quantum mechanics, when we have a particle that's really small, we cannot know both quantities at once. Unlike a really big object like a rock or a truck. For the small particle, that's not possible. Okay? So I gave us a hint here. When given an uncertainty as a percentage, we have to convert it to a fraction by dividing by 100%. Okay? So the uncertainty of the velocity, we then obtain it by multiplying this number by the actual velocity. So when we're given the uncertainty, we multiply the velocity by this percent, and we can find the amount of uncertainty in our speed. Okay. So to avoid using velocity, confusing velocity with frequency, we'll call U velocity and V as nu as frequency. Okay. So the equation we want to use is this one right here. So I may not have gone over this equation, but it's delta x, which means the change in x, or the uncertainty in x, times the change in position, okay, must be greater than or equal to h over 4 pi. Okay. Okie dokie, let's see here. Okay. So So I wanted to go over what h over 4 pi is, but it might be... Okay. So this value here is a constant. So basically it tells us that there's a certainty to which we can know the precision and momentum of the position and velocity of a particle both at once. So it's equal to this constant here, h over 4 pi, which is Planck's constant, determined and divided by 4 pi, which is so for our purposes, just think about this as a constant, that it's a limit to the uncertainty, or as a limit to the certainty that we can know both the velocity and the position of a particle. Okay? So it's really small. We can't know both of them at once. So another way we can think about it is delta H. Sorry, I get my letters mixed up now. Delta X times delta P equals h over 4 pi. All right. So when we do this, we can say, okay, my delta P, okay, is equal to delta m. So momentum is equal to mass times velocity, right? Delta m times delta v equals, so we know the mass pretty well, right? So we don't need to put a delta sign in front of there. We could just call it delta v. And when we do that, we get delta v equals, so 1.5 as a percent is 0.015 times the velocity here, 2.06 times 10 to the 6 meters per second. All right, so if we do that, we get the uncertainty and the velocity, which is 3.1. 3.1, let's see, is it just 3.1? Let's make sure here. E to the 6 times 0.015. Okay, so that's about 3.09 times 10 to the 4th. So let's change that a bit. So 3.09 meters per second. Okay, so there we go. All right, then now we have to calculate delta P. So delta P will equal m delta V. And the mass of electron, so let's, I'll give you this value, but the mass of electron is 9.109 times 10 to the negative 31st kilograms. So a very small particle. Okay, and then when we multiply by the velocity, we get 3.09 times 10 to the 4th. Okay, so if we solve that, we get approximately 9 e to the negative 31st. We get 2.81 I guess since it's 2 sig figs, let's just keep it. Actually, it's okay. Let's just keep it 2.81. 2.81 times 10 to the negative 26 kilograms per meter times meter per second. Okay, so that's momentum right there. All right. So now we know that delta x, we could solve for delta x. If we rearrange the equation for our uncertainty here, delta x equals h over 4 pi divided by delta p. Okay. So in this case, we need to turn joules here. We know that 1 joule equals a kilogram per meter squared second squared. Okay. So we can change our value here for Planck's constant from joules per second into, let's see here. Oh, sorry, it's per second squared. My apologies. Right here. So when we put in the units for Planck's constant, it's going to turn into this. 6.626 times 10 to the negative 34 kilograms per meters squared per second. So it's per second because remember the usual units for Planck's constant is joules per second. But if we substitute kilograms per meter squared per second squared times second, this will turn into per second squared right here. Kilograms meter squared per second. Okay? And then if we divide everything now by 4 pi times the value of momentum here, which is 2.81 times 10 to the negative 26 kilograms per meter per second squared. Oh, sorry, per second. Sorry, I keep getting that mixed up. Okay, so now if we solve for this, we will get 1.9. So the kilograms cancel, and then you're left with meters. So we get 1.9 times 10 to the negative 9 meters. Okay, so I kind of messed up on the sig figs here. So let's kind of go back and just put 2.8, and let's put this as 3.10 because the 1.5 has only 2 sig figs. So let's just do that. Okay, sorry about that. Okay, so this actually equals to 1.9 times 10 to the third picometers. So what this is saying, what this is telling us is that the uncertainty in the position of the electron is approximately 10 atomic diameters. So that's a lot. So that uncertainty is, so you see here, we can't know the certainty of both the speed and the precision. Sorry, why I keep saying precision? The position of the small particle. So it's impossible, almost impossible. There's a certain limit. You know, I wish technology had advanced where we could, you know, detect the electron, but we just can't. Okay, so that's how we would do a problem with uncertainty of the position of an electron. Okay, so now we're getting to more concrete, well, not concrete, abstract topics here. So now let's talk about the wave function, okay? The Schrodinger equation. So the wave function, so the last part of our quantum mechanics, we'll deal with the famous equation of the wave function of an electron. So a wave function is pretty much, it describes, it's tried to describe the nature of the electron in an atom. Okay, it's a mathematical function aiming to describe an electron in an atom, like its behavior. Okay, so the wave function takes on the symbol psi. So due to some very complicated mathematics and such, we will not discuss the equation in length. So, but if you took the operator of the wave function of an electron and acted on it, you can calculate the energy of the electron. And if you know the wave function of all the electrons in a system, you can calculate the total electronic energy of a system's electrons. Okay, so one thing we should do is that the wave function uses 3 variables to describe the position of an electron. So, you know, like we usually describe things in 3 dimensions, an x, y coordinate, and then usually have a 4th coordinate to describe or fourth variable to describe objects in motion, right? 3 will specify the coordinates, its position in space, and 1 variable to represent the time of an object, right, will be a specified location. So let's take this example. The captain of a ship is trying to intercept an enemy submarine. You would need to know the longitude, latitude, and depth, as well as the time it will take to be at a certain position, right? So you will use some very fine equipment to determine, predict its location, and what time will appear at a specific location, right? Okay. However, with electrons, we ignore this contribution of time because of the Heisenberg uncertainty principle. So for the wave function, we just focus on the location of the electron. So an important part of the wave function is that if we square the function at any given point, we can find the probability of finding the electron at that point. So usually when we use psi squared, so if you go on to like pure chemistry route or pure physics, quantum physics, you'll learn about all these quantum mechanical equations and that sort. So I'm not the type of person to talk to you about actually this. We're actually going to use this information to describe electrons and atoms and how it relates to the periodic table. But we're not going to talk too much about anything beyond that. So that'll be the point up to what point I talk about the electron. Okay. So basically, when we solve these, when you solve a wave function, what you're actually solving, what a solution to the wave function is called an orbital. Okay, and there are regions of space that we might find the electron in the atom. Okay. All right. So we can describe these solutions with a set of quantum numbers that describe the wave function for each electron. So these quantum numbers describe, where exactly the electron is in space, but it doesn't tell us like where it's going to be at a given point in time. So when you learn chemistry, you're never told like, oh, okay, it's in this orbital, but it's in this exact point on this orbital, right? We just say it's somewhere in the orbital. So we know its location, but we don't know exactly where it is at any given point in time because we don't know the speed of the electron. Okay, so we think the speed could be like, okay, electrons may be moving at the speed of light, but we don't actually know that. What we can say is just the location. So it's just this kind of paradox or like kind of thing we can't really reconcile in chemistry because the smaller the particle, the harder it is to kind of predict where it will be because the harder it is, we can't even see it. Okay, so that's kind of the thing we kind of have to accept. Okay. All right. So next we'll talk about the quantum numbers. Okay, that describe the wave function for each electron. Okay. So when we solve the wave functions, you solve the wave function, you solve the Schrodinger equation, you get what we called the solution to that is the energy, so a particular energy, and this tells us why electrons have different energy levels. It's because they're located in different orbitals, and those orbitals are at different positions or different distances from the nucleus. So that's why we talk about these quantum numbers. Okay, so when you learned about the quantum numbers back in like high school chemistry, it may have not been, it might have been, very hard to grasp, but here I hope when we talk about it, it'll be a little bit easier. Okay, so here are the orbitals. All right, so we have three coordinates or three quantum numbers are used to describe the orbitals in which electrons can be found. So they're like coordinates on a map, right? So you have the x value, y value, and then the y and the z value. So the first of our coordinates is the principal quantum number. Okay? The number describes the size, the relative size of the orbital. Orbitals where n equals 2 are larger than those where n equals 1. So this tells us the energy of the orbital. So the 1s, for example, if we look here in this picture here, we have the 1s, the 2s, and the 3s. So we see here that as you go from the 1s to the 2s to the 3s, you increase the number of nodes. So nodes are regions of space in the atom or the orbital that you'll never find. The probability of finding an electron is 0, and that's I don't really know how to explain why that is, but I have a feeling it has to do with like mathematics. Some sort of it has something to do with mathematics, and it's something I can't quite explain. But if you think about it, as you move further away from the nucleus, there's going to be some spots, some regions of space around the nucleus or in the atom that, you know, the electron, remember, the atom's mostly empty space, right? So there's probably going to be some spots where the electrons just won't populate, and that has to do with the fact that it's probably out of the orbital's region of energy. So it's probably not going to be there. And so there's always, it's like a wave, right? When you have a wave, there's always a point where the wave changes sign. Like it goes from positive or negative. So that point where it changes sign, that's called like a node. So in any case, you're always going to have some position that has some nodes. Some orbitals have nodes. So it'll just be region space. The electrons are not just going to occupy. And that's because, you know, these orbitals, they can't really touch in an atom. They have to be separated by some boundary. Okay? So the second quantum number is L. L describes the shape. So one number describes the size of the orbital, and the other number describes what type of orbital you have. So it could be 0. So there are 3 types we will consider. So when L is 0, it's spherical, like these spherical shapes you see here. Okay, so let's stop the video there, and I'll continue in the next one. So I'll see everyone then.